What if I told you that the biggest names in AI, the ones spending billions to build trillion-parameter giants, just got humbled by two models that are lean, compact, and brutally efficient? It sounds backwards, doesn't it? We're used to thinking that bigger is always better. But in AI right now, the exact opposite might be true. The smarter path forward isn't stacking endless parameters. It's designing models that think better with less. And that's exactly what happened. BaiYu and MBZUAI just dropped models that aren't only fast and practical, they're openly available. No corporate lock-in, no API only, walled gardens. Anyone from a grad student with a laptop to a startup with a vision can grab these tools and start building right now. This moment feels like a turning point. Imagine the biggest boxer in the ring getting knocked out by a fighter half his size. Not because the smaller guy hit harder, but because he was smarter, faster, and landed precision strikes. That's what these models are doing to the current AI landscape. Now here's the real kicker. These aren't just theoretical lab toys. They can actually handle long reasoning chains, math, science, coding, even external tool usage, all while running at speeds that don't melt your hardware. So in this breakdown, we're going to explore two game changers: BYU's ERA 4.521b, a 3B, a sparse mixture of experts model that cracks the sweet spot between size and reasoning power. MBZUAI's K2 Think, a dense yet blazing fast reasoning model with an almost agent-like inference process. But don't blink, because each of these systems contains design decisions that could quietly rewrite how the entire industry thinks about AI progress. Stick around, because by the end you'll understand why these underdog models might not just compete with giants like DeepSeek and GPT-120b, they might outlast them. Section 1. BYU's ERA 4.521b, a 3B. Let's start with BYU's model, which they call ERA 4.521b, a 3B. Don't worry about the intimidating name. We'll just call it a 3B. What matters isn't the branding, but the architecture behind it. A 3B is what's called a mixture of experts model. Instead of activating every neuron in its brain for each token, it selectively routes which experts to use. Think of it like calling the right specialist for a problem. You don't drag every doctor in a hospital into the room just to treat a sore throat. On paper, it has 21 billion parameters, but for each token only 3 billion are active. That's the magic. It gets the power of specialization without wasting compute on unnecessary parts of the network. And BYU argues that 3B active parameters might be a sweet spot, small enough to be trainable and deployable, but large enough to handle tough reasoning tasks. They reinforce this with clever training tricks, like router orthogonalization loss and token balance loss, which prevent all the experts from collapsing into the same behavior. The result: diversity in how the model thinks, smoother training, and stronger performance across varied reasoning tasks. But here's where it gets even more impressive. Long context ability. A 3B supports a 128,000 token window. That's massive. Imagine feeding entire books, complex code bases, or multi-document analyses, and the model can still reason coherently. How did they achieve this? Instead of hacking it on afterward, they trained it in directly. They progressively scaled rotary embeddings from 10,000 to 500,000 during training, paired with memory-efficient attention and scheduling. In plain English, they taught the model from day one how to handle long text without frying GPUs. The training pipeline itself was laser-focused. Stage 1, text-only pre-training, gradually expanding sequence length. Stage 2, supervised fine-tuning on math, coding, logic, science. Stage 3, reinforcement learning, starting narrow logic math, then broadening to reasoning tasks. They even introduced unified preference optimization, a blend of preference learning and PPO that avoids reward hacking, where a model learns to cheat feedback instead of truly improving. And let's not forget, a 3B has structured function calling built in. It doesn't just generate text, it can call external APIs, use tools, and integrate with systems like VLM transformers. That makes it not just smart, but useful. Performance, rock solid. Stable accuracy on chain-of-thought benchmarks, strong math and coding, and competitive results against models much larger. And here's the big differentiator. It's open under Apache 2.0, anyone can use it, even commercially. Which raises a cliffhanger. If a 21B parameter sparse model can hold its own against giants, what happens when you push this philosophy even further? That's where MBZUAI steps in. Section 2. MBZUAI's K2 think, if BYU went sparse, MBZUAI went the other way, dense and disciplined. Their model, K2 think, starts from a 32B parameter backbone, and layers on a remarkably clever training and inference strategy. At first glance, you'd think, okay, just another mid-sized dense model. But here's the twist. The way they fine-tuned and structured inference makes it perform like something far larger. Step 1. Long chain of thought fine-tuning. Instead of giving the model only final answers, they flooded it with examples where humans solve problems, step by step. Math, code, science reasoning. The goal was to teach it how to think, not just what to output, and the results showed quickly. Even halfway through this process, accuracy on tough math problems shot up, proving the model was internalizing structure earlier than expected. Then came reinforcement learning, with verifiable rewards. Instead of rewarding it for sounding convincing, MBZUAI actually checked answers, right or wrong, objective, not subjective. They built a dataset called Guru, covering 6 domains: math, code, science, logic, simulation, tabular data. This reduced the usual problem of reward hacking, where models try to trick evaluators. The learning signal here was reliable, and it paid off big time. But MBZUAI didn't stop at training. They engineered the inference process itself to feel almost agent-like. Before answering, K2 think first writes a short plan, like an outline. Then it generates full answers, multiple versions, and runs them through verifiers to select the best one. The outcome: cleaner, shorter, more accurate answers. And that's rare. Usually, when models add steps, they get wordier. K2 think broke that trend, outperforming much larger models across math, coding, and science benchmarks, while producing responses up to 11% shorter. Benchmarks confirm it. AIME 2490.8, 3 AIME 2581.24, OmniHard 60.73, Live Code Bench 5 63.97, all while being smaller and faster, and with speculative decoding plus wafer scale hardware, it generates around 2,000 tokens second. That's production speed, not research hype. Even more shocking, MBZUAI released everything: weights, data, training code, true transparency. That's nearly unheard of for a model at this level. So here's the cliffhanger. If both BYU and MBZUAI can achieve frontier-level reasoning with models under 40B parameters, why are we still chasing trillion-sized giants? Outro. So what's the big picture here? We've been living under the assumption that progress in AI equals scale. More parameters, more GPUs, more billions. But these two models just cracked that illusion. BYU's A3B showed that with a sparse design, smart routing, and long context training, you can get reasoning power without drowning in compute costs. MBZUAI's K2 think proved that dense models, if carefully fine-tuned and paired with agent-like inference, can outperform giants while running leaner and faster. Both are open, meaning you don't need a billion-dollar budget to experiment. That's a tectonic shift, because the real breakthroughs won't come from the companies guarding their trillion-parameter fortresses. They'll come from the innovators building on these open foundations. But here's the part that should make you think. If efficiency really is the future, what happens to the entire AI arms race? Do the giants adapt, or do they collapse under their own weight? The industry could split in two directions: closed, oversized systems, locked behind paywalls, or open, efficient, transparent models that empower a global community. Which side wins may decide who controls the next era of technology. And remember, these developments aren't just for researchers and labs. They'll shape the tools you use daily: your search engines, your productivity apps, your personal assistants. Smaller, smarter AI means more accessibility, faster adoption, and potentially a world where AI isn't just in Silicon Valley's hands. It's in yours. So let me leave you with a question. Are we entering the age of efficiency, where small but brilliant models redefine what AI can do? Or will the giants double down and keep chasing size at any cost? Drop your thoughts in the comments. I'd love to hear where you think the future is heading. And if you found this breakdown useful, Make sure you stay tuned, because this AI race is only getting stranger.